I don't know. Welcome back. Everybody, welcome back. I hope that you had a great break, but it's time to get back to work, all right? I need you to focus up. I can't have you fucking around like this, okay, everyone? So just lock in. I don't know. OBS showed me a couple of like little pop-ups in the toolbar, but the that's not Diet Coke. This guy lives. That's vanilla Coke. OBS showed me a little toolbar, like pop-up, but the text was the same color as the toolbar itself. And so I couldn't read any of the text. And I don't know what it said, but it probably said something along the lines of, I'm going to stop streaming now, by the way. Because right after that, it just stopped. So that was fun. Welcome to the stream, Brainwashed. Glad to have you. Johnny, you've finished your thesis. That's great. Congrats. Best of luck on your finals. Making it to the finals is hard enough for anyone who's ever played the finals. Okay, so I wasn't wasting time though, because while we were doing all of that, I did have the wherewithal to start the compilation. Just so you know. Okay, so we were talking about the optimization that I was recently doing. Recently being still working on it now, but it works. I need to test it, and the thing is, we don't actually have a test. I won't test it on stream because that's not going to be as interesting. But I need to test it before it gets merged. But yet we don't have a way to test optimization passes on the IR right now. And so I need to, I don't know, figure out how I'm going to do that. I'll probably use this closure representation that we have and then do some sort of pattern matching on that. I'm not quite sure. Brainwash, don't want to sidetrack. Can you, for a couple of seconds, just show me how deep into this project you are? Depth, my depth in this project, Brainwash, I'm super fucking deep in this project. This is, I started it like 10 years ago, but the last 3 years have been like the latest iteration of this programming language. I've been working on it full time for almost a year and a half now. I quit my job at EA because my background's in game dev. There's a GitHub link, no questions needed. Yeah, I mean, take a look at the GitHub. It's the real deal. No, you're good. Yeah, I'm way deep into this though. Like a year and a half into doing this full time on just sponsorships and open source grants, and trying to get some. We're trying to get it launched. It's in alpha right now, and hoping to have a beta release at the start of the next year. And then trying to get some interested businesses to actually use this, so that way maybe they can fund me to work on this. That'd be nice. Making money would be nice, but it's not a requirement. It would just make things a lot fucking easier. A lot easier. Also, DJ Blue, good to see you, man. Hope you're doing well. I say as though we were not just chatting an hour ago. So, check this out. How much work was put in the project before it gained serious attention 3 years ago? Well, I mean, I had been tinkering with it for 7 years before that, Johnny. I didn't know, like, Jenk wasn't always a closure dialect, but it was always a Lisp. So, I mean, a lot of work went into that. Pat10, thanks for the sub, 2 months in a row. I appreciate that. Welcome. Welcome to the exclusive Jankster Club. We've not decided officially on I think the term is demonym of like what people are called who use Jank. I think we'll do that once the community is larger, but for now I've been calling them Janksters, which I don't know if it's gonna land well. but it's fun. But Johnny, for this iteration of Jank where it is a closure dialect, I have a you know what? I actually just have a fucking history document, which I've not been keeping up to date. But let's take a look. So yeah, I need to I need to put more in here, because I've had like other sponsorships and stuff. But yeah, so it started in C++, and it was like a C++ style Lisp that was statically typed and everything. And then I rewrote it in Clojure, had like a macro system and interpreter working, had a whole fucking continuous benchmark service. Then I rewrote it in Clojure again and changed it to a Clojure dialect. And then finally, I rewrote it in C++ as a Clojure dialect, this time doing just-in-time compiled C++. So from here on is like the latest iteration. I didn't actually mark when we hit 3K GitHub stars, because we're at 3.2 now. Not that I count, but I definitely do. And yeah, there's some other stuff. That's a good reminder for me to fill us in. I think it's really helpful to have this, especially like in, I don't know, 10 years. It's cool to just look back and see the different milestones when I spoke at different conferences, when when we got funded in certain ways, everything like that. Okay, so we've built the newer branch. Let me show you what we have now. So for those of you who didn't see this, I'll just do a quick catch up. I've finally utilized our IR to write our first optimization pass over the IR. And the goal is to be able to take all of these literals that we have, like 5 used in these 4 places, and to hoist them to the closest parent. And so this is the IR that we have, and we have like entry and if and else and all these different blocks. And they, a bunch of them, 4 of them, have these literal instructions for the value 5. And so we have literal for the value 5, for 28, for 21, for 9, and for 3. And that translates directly to C++. And so we'll see 3 is, here's our number 5. And, this is already showing the modified version. So spoilers, you'll notice that there are no other instances of 5. And so we've won because I have the optimization enabled right now. But we're still showing the IR before the optimization. I've added this other flag here. We can change this to 2. And it's going to show us the IR after the optimization. So checkity check. So we got V3 is our 5, just as it was. But check out this guy. So this guy you can call it, like, you can see them by their really ugly naming, because the way the code's written right now, like this helpful VN naming is not available. There's a to-do for that, so we can get into that. So instead we're just using basically gensim to get this, but ignore that for now. What we ended up doing was these other literal instructions that we had, and we can see one here, we can see this here and this here. We ended up knopping these out. And so we replaced them with nop instructions. And these nop instructions, when you do code gen on them, like they don't amount to anything. In fact, we'll end up having another IR pass that's just going to remove these nops as well. But it's a really helpful way to be able to update the IR in place without affecting the allocation of all of these, because these are all stored in a vector. And if I were to just like actually remove it while I'm doing, you know, all my iterations and everything on these optimization passes, that might end up invalidating some pointers to some values. As well as indices to values, and it just gets messier. So instead, we just convert those instructions. We replace those instructions with nop instructions, and then we'll have a pass at the end that just cleans all those up, which we don't have right now. But in CodeGen, we just ignore the nops anyway. So what we end up doing is we build up this reverse post order list of a depth first traversal, depth first post order traversal of the whole graph. And the graph is all the different blocks. So entry and if 0 and else 1 and if merge 2 and so on. All of these different blocks, we look at how they're connected to each other. And then we traverse that graph and we build up this, this list, which is our RPO list, our reverse post order list. And this is basically, we use this list for depth, because the higher you are, like the further you are to the left of this list, the higher you are in the graph. And we see that because it starts with entry, and like our whole graph starts with entry. And if merge 2, if we take a look at that, that's the guy that actually has our return. It's like, this is the very end. None of the others, you'll see this one ends in a jump, this one ends in a jump, this one ends in a jump, this one ends in a branch, this one ends in a branch. None of the others have a return. So it makes sense that if merge 2 is at the end here, right? And then all these other guys in the middle are just like, you can get to them through various branches and whatnot. So the first thing we do when we want to build up the data structures for understanding these graphs is we build up this RPO list by traversing the graph. Then we have to build up our dominance. And so we have this immediate dominant map. And that basically says, for each block, what is the block that's like right above me? Okay, so for entry, there's nothing above entry. Its dominator is itself, and dominator is like a compiler. Well, it's not specific to compilers. I think it's specific to like graph theory shit, but it's definitely used in compilers. But entry just dominates itself, and something is dominated if every path to it. So like, I guess the formal definition is A dominates B if every path to B goes through A, okay? So you need to go through entry in order to get to if 0. You need to go through entry in order to get to else 1. You need to go through entry in order to get to any of these. And so entry dominates all of these. But is it the immediate dominator? That's the point of this map, is to find like the next, like the closest dominator. And so that's what this map is, and we get that by traversing the graph and then taking a look at this RPO in order to measure depth, and we end up with these two data structures, which are very useful when it comes to reworking instructions in our graph. Because if we take a look at the we don't have that here. But if we take a look at the output, so this is our pre-optimized graph. We have these literals. If we take a look at these, like, we want to know, okay, so we have 5 here, and we have 5 here, and we have 5 here, and we have 5 here. We need to know, like, what is between all of these 4 blocks that refer to 5, what's the one that dominates them all? That is basically the answer for, like, how we said we wanted to find, like, the lowest place in the graph that we could put it that's high enough to cover everything. And that is answered by having this dominance map, the immediate dominator map. What do you think about possible optimization such as removing unused results? The addition isn't performed. Yeah, for sure. So that's called dead code elimination. And so LVMIR is going to do some of that for us, but I imagine that we will have dead code elimination as an optimization pass in Jank as well. The problem, like the necessary step in order to get to it, is you need to understand which functions are pure and which ones are not. So if you have a pure function, then and you don't use the result of it, then very clearly it's dead code. So like +1, 2, that's a pure function, and the result's unused. No need to do the work. But if you call foo with 1, 2, then, well, is foo a pure function? Hard to say, right? Especially if foo is through a var, and vars can be redefined. And so that's not an optimization that you can do for normal closure calls unless you have something like direct linking enabled, because then you'll know, okay, this var is not going to be redefined. It can't be redefined. And so then I can take a look at the function that's inside of it right now and decide if that function is pure. Will optimization passes be extensible from user code? Hey, Fromophobic. I hope you're doing great, man. Maybe. You're not the first person to ask for this. And actually, I was talking to a Clang dev recently, and he saw the closure representation of the IR, and he's like, oh, that's like a reflection layer. Are you going to have people write optimization passes in Jank itself? And it's not like, I think we could support it, but it's not like a big goal right now. Somebody asked this in Slack, and I thought about it, and I outlined like how it could work. You know, you could register functions that just hook in to the optimization pipeline, and it could work. Now the problem is, although I'm rendering all of this IR in like a closure-y format, this isn't really closure data. This is just a nice rendering, but this isn't all of the data. Like, we don't represent types as strings like this, for example, right? Instead, we have pointers to the Clang AST, and there's a ton of Jank AST stuff and Clang AST stuff, and it's all like super C++ heavy. And of course, Jank has that seamless C++ interop, so we could, in theory, still do all of this from Jank. But it's not like you're just going to be doing nice data transformations over, and pattern matching over this closure data, because it's not actually represented as this. I don't actually think we want to represent it as this in terms of performance either. But yeah, you're right. You're right, DJ Blue, that if ever a normal defn is not enough, then using, writing a C++ function and calling that from Jank is going to be your golden approach. Speaking of golden approach, hey, Golden Lion, what changes in Jank compared to Clojure? Jank runs on native, and instead of interop with C++, instead of interop with Java, it has interop with C++. Instead of being written in Java, it's written in C++. So Clojure JVM makes sense if you want to run on the JVM and interop with Java libraries. And Jank makes sense if you want to run on native and interop with C and C++ libraries. Yeah, I mean, Clojure has FFI, but FFI is like watching porn compared to seamless C++ interop, which is like getting laid by somebody who wants to fuck you. There's a very big difference. Maybe that's not a great analogy. I think it's a great analogy. It's just FFI is just like it's not the real thing, Like it's first off, FFI goes through C, goes through the C ABI, which means that you lose all of the richness of your data types. You lose all of the richness of everything. You lose all the richness. And that's why it's fake. It's just really watered down. I mean, if you've done FFI and Clojure with a C++ library, then you'll know. So, for example, if you're working with a C++ library that takes in standard string or standard vector of some type, you can't. That doesn't work through FFI. Because that's not valid C. You just have to turn that into a pointer, and probably a pointer to void, which is a completely untyped pointer, because you're not going to be able to express templates in C either. So you can't have a pointer to a standard vector of something. So you'll have a pointer to void, at which point you have completely thrown away every ounce of type information that you had. And you're just working with give me a pointer to some data, which on the other end, I'm going to cast to to something and assume that I'm right. It's an awful experience. It's an awful experience. Don't do that. Instead, in Jank, if you're working with a C++ library that works with standard vectors, you're just going to use standard vectors. You can stack allocate them. RAI is going to work as it should. Destructors are going to be called when they should be. And virtual member calls work. Template instantiations work. All of this is just in time compiled. Throw, catch, C++ exceptions. It all works. FFI supports none of that. None of that. Function overload resolution also works. FFI does not support that. Yeah, FFI sucks, man. Anyway, I'm gonna quit shitting on FFI and move on. So we have a working optimization pass, and what we're doing is we're taking those literals that were duplicated and we're knopping them, and then we're lifting them. So we'll see that there's a knot here that has this special name. And this is a neat one because you'll see that knot is used right here in both of these cases, right? Now both of these knots are in different blocks. So I'll show you the IR that we have here. We have knot right here in else 15, and we have knot right here in if 14. There is no common, like, for the 5, we had a 5 in entry, and then we also had 5s elsewhere. And we could basically just keep the 5 in entry and then remove all of the other 5s and replace the uses of the other 5s with the 5 that we have from entry. That was really handy. But in the case of knot, this knot here and this knot here are in just 2 separate branches that are next to each other, because the if 14 and the else 15, those are for the same branch. And so, like, that is this if right here. We have a branch that then goes into a block here and a block here. So what we need to do is we need to find the common parent and then create a new literal instruction. And so that's else 1 right here. You'll notice that else 1 has 2 instructions in it. And if we run it and we show the optimization, we'll see that else 1 now has 3 instructions in it. And the first instruction is this guy right here. And you can tell it's different because it has this different name. This is where we brought the knot up to. And then we can use this knot in both the if and the else down here. So this is where hoisting, like, comes in as well, where we've like taken the knot that's used in these 2 places, we've lifted it up into the common place, created a new instruction there, and then we can use that in the 2 lower places. Interop equals strong control to embed a lot of host behavior. FFI is very limited layer of information exchange. Yeah. I mean, that's what I said. Except with a very different metaphor. Analogy, not metaphor. Okay, so this is one optimization pass written. Now, there's another one that I want to write on stream today with all of you. Assuming we can make it there. And in order to do this, let's take a look at the optimized IR that we have here. And I'm going to delete this guy, and then I'm going to make a new tab, and then I'm going to bring this guy in. Let's take a look at the optimized IR that we have here. Optimized meaning that we've run our one optimization pass on it, not that it's fully optimized, because I will not claim that, because I specifically know that there is more work for us to do here. Now let's take a look at what else we can do with this. And I have one thing in mind going into this stream that I know we want to work on, and it's actually the same thing that I have written right here. After deduping literal instructions, we want to dedupe var derefs. So when we call printline right here, we're calling printline from 3 different blocks. So here's the then for this if, here's the then for this if, here's the else for this if. That's 3 different blocks where we're going to be referring to then. And we're going to be referring to printline. And so the printline we can see right here. Here's our first if, and I'm just gonna search on this guy. So here's our first if, and now we have our second if. We have the then for the second if, and we have the else for the second if. And so we have a var deref happening in 3 places. Johnny, this is, I'm glad that you bring this up, because now we get to talk about some interesting stuff. So Johnny says, but you cannot technically do that. And this is something that I have been thinking about for months, literally months, as I've been planning this IR work. Before I was doing it, back when I was I don't even know what I was working on a couple of months ago, but it was important. And now that I'm working on the IR stuff, I actually get to utilize this. But here's the thing. Hear me out. So the reason that we have var derefs is so that vars can be redefined. And the root of a var can be changed. And then the way that it works by default is whenever you use a var, you get the latest value of that var. Now, there's nothing in Clojure's documentation or like reference documentation or like rationale or anything like that I found that says the granularity that var derefs need to happen in. And so for me, I was thinking about this, and I know that var derefs, based on the research I've done and the profiling that I've done, var derefs are very expensive. And this is because they require synchronization. In order to get the root of a var, so we can see var, what we end up doing is a deref on this guy. So we'll do a deref here, jump to deref. Yeah, so in order to get the deref, we have to, so we do a read lock, and we do a lock on this, and then we grab the value from it. Now it's also possible that we have a dynamic binding. And so in which case that's a thread binding. We have an atomic bool, which is then used to store whether or not we have a dynamic thread binding. So that means that in the best case where we don't have a dynamic thread binding, we have to check an atomic bool, and then we have to lock a mutex. And in particular, because we're using a read-write lock, which I don't know is the best mutex for this necessarily, but there's synchronization that needs to be done. And we have to do these. Clojure JVM has direct linking. We're not talking about direct linking from homophobic, but we have to do these derefs every single time a var is referenced in code, right? So when you say print line, when you say print line, when you say print line, every single one of these ends up getting a var deref. And the reason that we do that is so that if the var were to change between any of these lines, the next line would always get the next var. Now, as Fromophobic linked in chat, there is a compilation mode where you can disable this entirely, and you can just say, I don't want vars to be replaced, and so go ahead and always just eliminate var derefs wherever you can. That is like one way of doing this. It completely that works great for like AOT compilation. If you're not going to be doing any var redefining during the runtime of your application, then you can get better inlining and type propagation, everything like that during compilation if you enable that for AOT. However, when you're doing JIT compilation and you still want to be able to interactively redefine things, there's what I'm trying to get at here is I don't think that it's black and white. Right now in Clojure JVM, it is black and white. It's like, yeah, well, either we're going to do a var deref on every single usage of the var, or we're not going to do any var derefs. And that is like the first one is the default mode of operation. The second one is you have direct linking enabled. But I think that there's a gradient. I think that there's like okay, well, how often do we actually need to do var derefs? Because let's take a hypothetical example, right? So let's say you have some like game loop, okay? And so as part of your game loop, I don't know, let's just say you're doing a loop here, and then you would say like, if we're are we done? You have your game state. You have your game state like so, and if you're done, then then you'll quit, sure. And if you're not done, then you're gonna go do some stuff, right? And so you're gonna say like, okay, so let's update things, and that takes your game state, returns you a new game state, right? And then finally, you're going to render things, and I guess you're then going to recur. So let's say that this is your rough game loop. Anyone who's written a game is getting what I mean. Anyone who's not written a game, hopefully this is clear. Now this means that as your game loop is running, and sure, you may have some like sleeping in there or whatever to make sure that you're hitting capping frame rates or whatever. It doesn't matter. As your game loop is running, there are some functions that you might want to change, like update things and render things, and done. Maybe even quit, right? But in particular, done and update things and render things. These run every single tick, every single loop iteration of this game loop, right? And so the idea is, if you change render things, then next iteration you're gonna want the new render things function to be used. That's important. That's like crucial to interactive development. This would allow you to redefine render things from your repo client, and then your whole game, without restarting it, next frame is going to render things correctly. So if you were to let's say, we're not talking about jank optimizing things, anything like that. If you do this in Clojure normally, every single one of these guys here is a var deref. And so we're going to deref done, we're going to deref update things, we're going to deref render things. For this particular game loop, that will work fine because we only actually refer to these things once, and that's not really a concern. But when you take a look at something like something like this, where we're using println here 3 different times inside of this let, we have to ask ourselves, do we care, realistically, do we care about println changing in between these calls? And my answer to this is no. No, we do not care. I don't care. I don't think it's reasonable for somebody to care about this. But if they do, to be fair, if they do care, then this particular optimization, first off, is only enabled with O3. And secondly, can be disabled explicitly. So if for some reason it doesn't work for you, you can disable it explicitly. However, I think the way that we're going to do it is that this is going to work basically in every case. And if it doesn't work, it's because you're doing something really weird. And so what we're going to do is this. We're going to say that var, and this will be documented in the Jank book as well. Var derefs with O3 enabled will have the granularity of one of two things. It will either have granularity at the function level, which means that once per call, you're going to get the latest value. Or If there's a loop inside of that function, then the var deref will have the granularity of the loop. And this, as far as I have like reasoned through all of the different ways that you can write things in Clojure, this is going to cover both of these cases, because there are only two ways to loop in Clojure. There's using a loop, and then there's using recursion. And so the recursion case, that's going to be the function, like the function level granularity. And so in this case, we can dedupe these three derefs into one deref, and we'll lift these up to the closest dominator, just like we did for the literals, right? And then in the case of the loop, we're not able to hoist these out of the loop. They have to stay in the loop, but we can dedupe them within the loop. And so if we had something like update things game state, and then let's say we did like update things false, and then update things true. I don't know what that flag does, but let's say it does something. Then here we would not do two derefs for this. We would do one deref, but it would be within the granularity of the loop. And so each loop will end up refreshing update things. Does this make sense? And Fromophobic, what do you think? And anonymous functions would create their own scope. Anonymous functions are just functions. So anonymous functions in any sort of var derefs inside of an anonymous function would operate at the function granularity, unless there's a loop inside, in which case we operate at the loop granularity. So that applies regardless of whether or not the function has a name. And as far as Jenk is concerned, there's no difference. As far as Clojure is concerned, there's no difference between an anonymous function and a normal function. They're just functions. Just double checking. Yeah, for sure. By the way, what's your opinion on read eval? Clojure core read can process dangerous reader macros by default, which is technically unsafe and shouldn't be used in 99% of cases. I think that I don't like that. Yeah, seems reasonable. That's what I think. and this is the exact sort of thing that the IR that we have enables us to do. It's the exact sort of thing that becomes straightforward to write as an optimization when we have this IR. So let's do that. Let's do that right now. Let's write an optimization pass that is going to look just like that. And the nice thing is, whoops, I'm going to delete that. The nice thing is, it's going to be pretty damn similar to our hoist literals pass, but it's a little more complicated when we factor in the loops, right? We have these we have these constraints that we can't do this optimization across loops. The only thing I can imagine is unexpected behavior and macros, but I can't think of a concrete problem. I don't think so. Macros are just functions that are called at compile time. So I don't foresee any issues with that. but we'll see. Like, I have no issue. Like, this is just an optimization pass. We're going to hack it together. It's going to work in an hour. And then we're gonna see how it works on everything, right? I'm just gonna yoink all of this code. I don't know how much of this we're gonna share. I don't know if this comment block is gonna make sense for what we're doing, so I'm gonna comment everything later. And I'll also keep the to-dos because this naming here, like I don't like that. I want that to change. I mean, you're generating code where you end up with one logical call site, but it's implemented as multiple actual call sites that get executed over time. What? Generating code where you end up with one logical call site with retries, foo. Uh-huh. Sure, but that's not a var deref right there. That's just, oh, you added another backtick. As the macro receives it, that's not a var deref. Foo is not a var deref, assuming with retries is a macro, right? Foo is just a list. Macros don't receive as much as people call Lisp code ASTs. That's a real, that's not, they're not ASTs. They're parse trees. And macros receive parse trees. The data that macros return is parse trees. And so we're not even dealing with var derefs at that point. But it could expand to multiple calls to foo. Yeah. Doesn't matter, bro. I don't see any concern there. If I'm wrong, then keep on me about it. But I don't think I'm wrong. I think it's all good. I've dedicated many showers to this. Okay. Let's see. So we're gonna do a string. Also, we don't need any of this. And then this is string. Yeah, and so here, if we have a var deref, then give me a var deref, and then qualified var. Nice, we do have that. So we have all the info that we need. Cool. So this is it. This is the function that, well, that's not this. This is half of it. Where this is just going to take our IR function. I'll show you. And then we're going to loop through all the blocks. We're going to loop through all of the instructions in each block. And if it's not equal to, like if the instruction is not a var deref, then we're just going to ignore it. If it is a var deref, then we're going to collect, and now we have collect var derefs. We're going to keep track of, so we have build a map from qualified var to, and what we have here is this vector of identifier, which is block name and instruction name. Block name, instruction name, because we're going to need both of those. Okay, that's that. Now, var derefs. So for our function, hoist var derefs, and var derefs. Cool. This stays the same. So in this case, so we have all of these occurrences, and for each one we end up, we have, to put this in closure terms, we'll have something like a closure core print line as the key, and then the value is going to be a vector, and that vector is going to be something like, so we'll say, okay, entry uses this, and it's v2. Yes, so it looks like this. So the occurrences, and this is this outside vector here, we may have multiple occurrences. So like if 9 may also use this, and it's called v17. And so this is all of our uses of this particular var deref. Now, if the occurrences is less than 2, that means it's 1 or less, then we don't need to do anything because there aren't multiple. And so in that case, we'll just leave it. We'll just leave it exactly as it is, because there's only, in this case, there's not going to be 0. So that means that there's only actually 1. It makes sense to just check equals 1. I think so. I like to use less than. This is kind of an odd thing. I don't like using greater than. I don't like using greater than because it puts the greater thing on the left and the lesser thing on the right. And I like, whenever I represent things, I just represent them in terms of less than instead. So I'll do like if the size, so instead of checking like if the size is, I guess you would do like foo.size. So thinking about things in terms of greater than is always odd. I have to like invert my brain. So I'll say like if it's greater than 2, then but I would end up just saying like, it breaks my brain. So I just use less than. Well, I'm catching up on chat. You said something about loops. Not sure if I missed it, but what if I write this while true print line process read line? Yeah. So while will expand to a loop, and while is just a macro. So loops and functions are the granularity, and we're not allowed to hoist derefs out of loops. So your case, Johnny, would not break, and it would still be reactive to var derefs. Also, you're not just changing if another deref is happening, you're also changing when the deref is happening. Yes. I'm taking a look at your code here from Homophobic. So you have a dynamic n, which is 42, and you print it, and then you bind it to 43, and then you bind it to 44. Oh, wait. I mean, your bindings there do nothing. I don't know what you're trying to do there, because your bindings don't actually do anything. They're not printed, they're not returned. So is your concern about the deref of the of n fromophobic? Hey Dayloop, welcome to the stream. I hope you're doing great. Okay, yes. Then yes, exactly. You're right. So if your concern is about n fromophobic, then we just don't do this for dynamic vars. Okay. Yes. Got it. Yeah. So we don't do this for dynamic vars, and we don't cross loop boundaries. Yeah, another one I've thought of is like, what if there's a def inside of the function, and you want the code to be reactive right after the def happens. And this is just one of those cases where like, okay, well, if you're actually doing that in production code where you're running O3 and you still want that, def in the middle of a function, then you just disable this optimization. Or just like, don't do that, because that's weird. Like normal Clojure code doesn't have def in the middle of a function to redefine something that you then want to use the newest value of in that function. Like I'll put a def in a function to define something for like, when I'm reppling in and I want to grab the value from a function and put it into a def so I can inspect it or work on it or something like that. But I'm not redefining a function in the middle of another function and then expecting to use that redefined function for the rest. If I want to do that, just disable this optimization. I think the vast majority of code, this is just going to work well. It's just going to work well. Whoops. Sorry for the black screen. Otherwise, it's not much different from using direct linking, which people use regularly. Yeah, I think that this is kind of like direct linking without the big sacrifice, like without completely sacrificing interactability. So I think that you could still you can still reasonably do like REPL driven development with this optimization enabled in every like normal case I can think of. And that's a win, because it's like, okay, so we're going to allow you to do REPL driven development, but we're also going to generate just much more efficient code. And in terms of how much more efficient, well, we're going to see, aren't we? Because we're going to write this and then we're going to take a look at the performance difference with this optimization enabled and with it not enabled. And then we're going to find out, aren't we? Okay, so we collect all of our var derefs, and I want to change this to qualified var, and then we have our occurrences, and so if we have only one occurrence, then there's nothing to dedupe, and then otherwise we need to grab all of the blocks that actually own one of these derefs, and so... Okay, and then we're looping through each one. So we have, in this case, one qualified var. We'll take a look at how many blocks are referring to that. In this case, we know that it's 2 or more. And then we do the LCD, the least common denominator between those blocks, in order to try to find the target block. So we find the target block, and now we need to know if that block contains the instruction. I guess we don't do that just yet. Instead, oh, we do that. Yes, that's okay. That's exactly what we do. I was like, wait, I thought that's what we do next. Yeah, so we loop through we loop through all of our occurrences, and we check if the block name is equal to this least common denominator. So we found the block where this should go. That is going to be common among all of the blocks that we need it to be available in. And then we just want to check, do we already have one in that block? And if so, we set our canonical name to be the instruction name of the instruction that's in that block. And so in this case, it'll be like, okay, canonical name is going to be equal to v2 or v17. Now, if we didn't find it, then that means that like the scenario here where not is used in these two branches, and there is no like commonality between these two, we needed to lift it up to here, but it's not there. Like there is no not that's available there. And so we need to create a new not literal there. And then we need to replace these two with the one that's lifted up. And so that's what we have to worry about here. So we end up creating a new canonical name. We have a to-do to not generate this ugly name here, but to generate one that follows the incrementing V's that we have here. I'll leave that to do because I still need a better system for that. And then we figure out where to insert it. And so right now, like what I have is that we're trying to insert it after parameters and captures, just because at the start of some of these blocks, we have all of our parameters and all of our captures. And it's just nicer for those to all go first. It really doesn't matter in terms of the implementation. It's just kind of like an IR organization thing. So this ends up being very similar to this hoist literal. So like, I don't know how much we're going to be able to just actually refactor this stuff out. Like maybe we can make this whole thing more general. But since we're like still figuring out how all of this is going to look, I'm finding the duplication for now, and then we'll identify the common patterns as we get more and more passes, and then we'll do what makes sense. But yeah, I'm okay with the duplication to start with. Okay, so now here's where we actually go in and we start adding our instruction. So we don't need to worry about. So we grab the first occurrence here. We grab the block that the first occurrence is in. And then we grab the instruction from it. And so what we'll do is we'll cast this to a var deref. Now, so here's an existing guy. So we're going to make a new var deref instruction. And so let's take a look at our instruction var deref. So the only thing that we need here is really a qualified var. So name location qualified var. So let's just do name location qualified var. And then we insert it. And then the rest of this is just going through the rest of the uses, the rest of the occurrences, and knopping them. And so what we end up doing is we go through all of our occurrences, and as long as the instruction name here is not the one that we stuck with, that's our canonical name, as long as it's not that, then we have to rewrite all of our uses. And so what this means is, let's take a look at our instructions here. So, so we have this print line here for v10, and this should end up being the one that we stick with, because v10 dominates if merge. No, it doesn't. If 14 is dominated by this. Hey, Sir Elfman. Oh, you know what? No. So, okay. So what we're going to have to end up doing with the way that the dominance works with this graph is that entry is actually going to get the goods. Let me get this guy out of the way. So entry is what dominates if 0, and if 0 has this print line, and that is going to be the common parent between all three of these, because they're each in their own blocks with no common parent aside from entry. So what we're going to end up doing, as far as I can see here, is we're going to end up adding a new var deref inside of entry. And then we're going to loop through all of these other var derefs for closure core print line, all three of them. And we're going to see, okay, so for this one, V10 is its name. And when we do rewrite uses, what we're going to do is we're going to have V10 and then our new canonical name. And so our new canonical name is going to be, we'll have something, it'll probably be about here, and it's going to have some ungodly, awful looking name like this. And this is going to be our var deref for print line. And we're gonna find V10, and then we're gonna rewrite all uses of V10 to be our new name. And so that means we're gonna go through and we're gonna search for V10, and we're gonna see, okay, it's actually only used in this place. And we're gonna rewrite this to be our G, and then we're gonna nop this out. So this will be some like gnop thing, and this will be a nop here. This is what's going to happen. This is what's going to happen. And I think we have everything we need. So let's save this. I think I need to hook this in. I need to make sure that this runs. So we hoist literals, and now let's hoist var derefs. And I need to include that var derefs like so. Let's take a look at our compilation. I'm just going to make sure that it caught all that. Okay, so we have an undefined reference to hoist var derefs because I didn't add it to CMake. So hoist literals var derefs. Oh, I'm excited. I gotta say, I was just telling my wife about all this before the stream. Like, it was a lot of work to get the IR in place. And so far, I've not been able to have fun yet with the IR. And yesterday, today, I guess today's Wednesday, this week, Monday, Tuesday, Wednesday now, like, I'm starting to actually write these IR passes and take advantage of the structure that we're representing our programs in now. And what a blast. What a blast it is. Actually, yeah, so let's see if this crashes. How do you do stack traces in Jank? Native stack traces kind of suck, but they do work. So we are able to print stack traces. There's Unfortunately, in C++, there's, I think in C++ 23, we just got like the first cross-platform stack trace support added to the language, but we're JIT compiling C++, which is which is not well supported when it comes to stack traces. And I've been working with somebody who has a stack trace library in C++, and he added some support for JIT compiled stack frames, but it's not his fault, but it's just not super reliable. There's more work that needs to be done there, probably with LLVM, and then also with his library to make that super reliable. It's much more reliable in GDB. So like the information is there. It just needs to, we just need to be able to get it. Oh, cool. Yeah, you implemented that yourself. That's nice. Good work getting that going. Okay, so let's take a look at, folks, we did this. It works. Wait, it runs, and our var deref is gone. Now we're not taking into account our two special cases, which is minimizing, like making sure that we don't cross loop boundaries, and then also not doing this for dynamic vars. We're not taking into account those. But in terms of actually just like alighting these, we've done it. Let me pull this into the editor so we can get some nice highlighting, and then I'll show you. And also, it looks exactly like I said it would. So we have a var deref here that was created, hence the ugly name, right? And that was because there is no, like, for the three places that these are used, they don't share a like, none of these blocks dominates the others. So we had to go up higher in order to find one that dominated them all. And that one was entry. And so we added this new var deref and entry. And then you'll see we have more nops from the var derefs that we ended up replacing. And then here you'll find, so if we just search for this guy right here, you'll find that the rewrite uses applied to this dynamic call. It applied to this dynamic call down here, and it'll apply to this dynamic call down here. So yeah, that's, again, like, I'm not quite sure how we can remove the duplication, but 125 lines, and we're able to clean this up. Now we just gotta, like, this is unfortunately not something that we can merge because, as we discussed, there are some tricky cases. So let's try to handle those. So the first one's easier, which is don't do this for dynamic vars. I think what we could do for that is just don't even collect dynamic vars in the first place. And so if we did something like intern var lit qualified var expect OK I want dynamic. We have a dynamic thing, right? Yes. Dynamic load. Okay. So dynamic vars, actually, rather than this, we're just gonna continue. Dynamic vars Okay. That handles that case. That wasn't so hard, right? Now we need to handle the more complicated case, which is looping. So as I mentioned, I don't yet have a way to test these optimization passes because it's a brand new system, right? I just wrote this first one for hoisting literals like this week. And then we just wrote this var deref one right now. And so I know that there's going to be a lot that needs to be tested, especially for the var deref one. Like we're going to need to handle all these different cases of, okay, so what if they don't have, like what if there is an instruction in the LCD of all of them, the least common denominator? What if there's not an instruction in the least common denominator? That's the one where we need to insert a new instruction and then rewrite all of the uses. And that applies to lists, literals as well as var derefs. And then var derefs also, we have the, okay, so what if it's dynamic? And then also, what if it's in a loop? So those will be tested, and I'll make sure that all that makes sense. But for now, we're just going to do manual testing. So what does the manual test look like for this? So we're gonna give ourselves a function, and so I think it's gonna be, we're gonna have a loop, and I think the simplest case is probably a print line outside the loop. And then a print line inside the loop. But let's do two print lines inside the loop. Okay. What about after the loop? You know, I think I'm trying to remember now what I thought about this. I was thinking that maybe if it contains a loop, I think what I arrived at was if it contains a loop, then we just don't fuck with anything. Because I think that is probably the sanest solution. Like that would definitely work. And it's going to be pretty easy to know like if a function contains a loop because there's actually a loop instruction. So we can just loop through the function blocks, see if there's a loop instruction. If there's not, then I guess there's named recursion as well. Those are the only two ways that you can loop. Recursion and looping. But yeah, like I wonder, so like we could definitely do that. And maybe that's a good first pass, but I just wonder if we did more. And DJ Blue, like you're thinking along the right lines. Like, so what if we also had a also outside? So in this case, like we can't save the print line. Like we can't lift this print line up above the loop. Because potentially in the middle of the loop, it changed. The granularity is because there's a loop here, the granularity is at the loop, the level of the loop. So yeah, I think maybe rather than trying to track like what's before a loop, what's after a loop, what's inside of a loop, and then like break those into sections, I think we just say, if there's a loop, then we don't do this. Named recursion. I'm not sure about named recursion. So we have this case. Now we also have another case where we do something like this. Done, false, if done, done, otherwise recur, like so. And we don't have this here, because recur needs to be in tail position. So in this case, do we allow the optimization pass to run? Since the recursion happens at a function level, I would think that we can still have function level granularity for this. And so I would think that this still can work. Hey, Marnix. Welcome. Nice to understand your philosophy on life around taking pills. You know, there aren't just pills though. There are also gummies. They even taste better. I think that this will work with function recursion. Let me know if you think otherwise. But let's do the loop one first. So we want to know if we're in a loop. We want to know if we have a loop in our function. Let me get rid of this. And so we're already looping through our functions and blocks here. I kind of just want to not loop again. So I'm just going to build a struct. That just has the details. And so this will be occurrences. Occurrences is what we were calling the second part of this. We'll just call it derefs. And then after this, we'll have a bool for whether or not the function has a loop. Okay, so what we'll say is, if we have a loop, then, oh, and also we need to change the return type here to var deref info. Yeah, so var deref info result derefs return result. Okay. Result dot has loop is equal to true. Now in this case, where we know that we have a loop, we don't even need to bother continuing to collect the rest of this stuff. So we can just return. We can just return. Because loops invalidate this optimization. So we're done collecting. I'm gonna put that in here because it says, so we're done. And we're only done if we get into there. Yeah. And so let me pull this derefs. And then what we'll do is we'll just say if var derefs has loop, then we're done. That's it. That's it. Chat, that's it. 150 lines. All right. So, oh, goddamn, right. Let's take a look. We have our, yeah. So we have our test here. Let's see what we've done. I want to grab the IR before the optimization first. Outside, inside, also inside, inside, also outside. Is that what we want? Outside, inside, also inside, inside, also outside. Yeah. Because we do the outside, we do the inside. Done is false. We do also inside, we recur. Done is true. We do inside, we're done. Then we do also outside. So outside, inside, also inside, inside, also outside. That should just be a song. Pretty good. Catchy. Okay. So let's do the two for this. So we have print line, we have print line, we have print line. How many of these guys do we have? We have 5 of these fuckers. Oh no, there's this one up here. That doesn't count. So we have 4 of them. 1, 2, 3, 4. Yeah, so we have 4 of them here. Now, all right, I just did that. So if we take a look at this, I won't copy it. So var deref. Okay, so we clearly skipped this. Like we didn't optimize this because it has a loop. We didn't want to optimize that. Didn't want to optimize that anyway. Now we'll do this one. So this one, I think we can still optimize because we don't have a loop. Like we have a recursion, but that recursion happens at the function level. And so even if we had a named recursion, such as something like this, right? That's totally fine as well, because that's just a function call at that point. We'll end up getting into the function again, and then we'll just reset the state for that. So let's take a look at what this looks like. Did I do a print line 1? Yes, I did. So this is going to be the unoptimized IR for this guy. Let's paste it here. So we have, okay, yeah, so this is where I'm wrong. Because what we end up doing is when we have named recursion in tail position, or if we have a recur in tail position, we translate that to a function level loop. And so we have this function level loop where we basically mutate the parameters with each iteration. And so when we're looping here, you'll notice that our recur is basically a jump. And we end up doing this branch set in order to mutate the variables as we iterate. And in particular, the variable that we're mutating is this done. So it starts off at whatever the parameter value was, and then when we recur here, we end up setting it to true. And then okay. So we don't get to optimize this case either. Hey, TwitchTD. Today we're writing optimization passes for our custom IR, and it has been a huge success so far. So we've already written one pass in this stream, and it works. It works really well. It works really well. So that means, unfortunately, that we're not going to end up optimizing this case as well. And so when we take a look at the generated code, yeah, we have a deref here of 550, and we have a deref here as well. And so those two derefs, that's the print line and the print line. And so both of those have a deref right on them because we have the loop. Because we have the loop instruction right here. Okay, so that's fine. That's totes magoats okay. So here's what I want to know. Here's what I want to know. Dominance. I want to comment out this stuff, and then I'm going to configure for release, and then I'm going to delete this, and then we're gonna compile and we're gonna chat. Because this is going to take about 4 minutes to compile. But I want to know, did this have an impact on our ray tracer benchmark? Because now we get to know. Now we get to find out. Don't you want to know? TwitchD, how are you doing today? What's life like in Twitch TD land? Also, what other optimization passes do we want to do? So we definitely want to do one. I think we could do it today, probably to remove the NOPs. Ooh, dynamic call. Ooh, a lighting self-assignment from Recur. That would be a good one, I think. That's another optimization pass that we can write. That should just be really easy. Yeah, that one's going to be even easier. Maybe we can write that pass and then also the NOP cleaning pass. Both of them today. That would be three passes that we write today on stream. I don't know, maybe I'm getting ahead of myself. I think we can do it though. Is the purpose of the NOP cleaning pass just to make future passes faster? The purpose of the NOP cleaning pass is, I think it would probably run last. And I think it's not about performance at that point from a phobic. It's just about cleaning up the IR. That way, if you're printing the optimized IR, it's just not full of NOPs everywhere. Cause yeah, like if I print the optimized IR, I just want to see like the smallest IR possible that is able to represent, you know, the behavior of the code. I don't want to see NOPs for where a bunch of stuff used to be. When your function returns bool, avoid calling truthy for if con. Oh, we already did that, DJ Blue. That's done so. That was done as part of the fib optimization stuff. Are you going to create benchmarking tests like example X is return to run under 1 second plus or minus 100 milliseconds? Maybe TwitchDD, but that's not on the docket. That's hard because that very much depends on the machine you're running it on. You can't really run that in CI. What we do have is we do have a continuous benchmarking suite, continuous in the sense that it runs every day from Kyle C, who spun that up for us. Is Jank fast yet? And this guy. It goes to the README for some reason. So we do have this, which shows Jank. Ooh, nice. That's a big win there for primes. And yeah, even bigger win for Ray. Ooh, nice. Yeah, recent work has been helping. I like that. So this is like we do have this TwitchDD, and I want to get more benchmarks added here. And these run on real hardware that Kyle owns every night at midnight. DJ Blue, was it expressed as a pass? No. The only passes that we have right now are the hoisting of our derefs, which we just wrote right now, and then the literal one, which I wrote like Monday, Tuesday. And so that was just represented during analysis. No, it was handled during IR gen. So we just did truthy right here. So DJ Blue, when we are generating the IR for an if expression, we end up checking the type of the condition. And if it's any jank object, then we generate a truthy instruction. And otherwise we just use the condition directly. Because during analysis, we already do logic to ensure that it's either a bool or it's a jank object, or it's something that converts to a bool. And so the bool conversion will be handled implicitly for us by the C++ type system, and then truthy is used if it's needed. Did you add binary trees benchmark? Nope. Nope, we don't have anything for binary trees. I don't know specifically what that what that benchmark would be. I also don't know if that's a practical closure one. That one's insanely intense for GC. Do you have a binary tree benchmark? Like, do you have such a benchmark written in Clojure? Oh, made by Boehm himself. In that case, it's going to be in C. Yeah, like, I don't know if that makes sense to translate to Clojure, because it's probably very bits and bobs, very low level, and Clojure works with, persistent immutable data structures. So I just don't know if that benchmark makes sense to write in Clojure, because the thing is, like, the benchmarks that we run, we want to run it in Clojure JVM, and we want the same code to run in Jank. So we would need to be able to represent whatever benchmark it is as like normal Clojure code with immutable data structures. From Rich himself. Also, hey Matt, bin tree 16 years ago. Yeah, but the problem with this is, like, let's see. Yeah, the problem here is it's using def interface and JVM type hints. And lots of JVM, like lots of just interop on these things. So, like, we couldn't run this in Jank right now because we just don't support def type and def interface yet. And the type hints are also not supported yet. But this is something that we could end up adding. Def interface? What are you talking about, Johnny? It's fun that you got IR opt pass up, and it reminds me of doing LVM opt passes. Very cool. Yeah, it is cool, man. This is very fun. Right, what were we doing? We were compiling, right? Oh, right, and then we ran into a compilation error. So that's, I guess, before we thought we were going to be able to have fun testing the performance of our new stuff, but it turns out we've just realized that our new stuff fails to compile Clojure core in particular. How can you even implement custom types? I mean, is the entire code gen and object model centered around a limited enum of object types? Or is it extensible? It's extensible. Yeah, I mean, to support things like def type and whatnot, you need polymorphism, And so you'll have a base object type, and then your custom types will inherit from that. And Jank didn't have that for a while, but it does now. But I just haven't built out those systems yet for like def type and def interface, stuff like that, because I don't use them. Like in my production Clojure code, I don't use all that object-oriented bullshit, because the whole reason I use Clojure is to not do object-oriented bullshit. And so like, and also when I see Clojure that's written with that object-oriented bullshit, I'm just like, all right, that's not what I use Clojure for. But, and like, yeah, it's going to look better in a benchmark, but that's not actually, you know, kind of, it's not how we write Clojure. In Rich's defense, this is the same exact reason why I'm adding like CPP def and CPP defen to Jank. The idea that you can reach into the host for performance if you want. And so obviously Rich is doing the same thing as well. And that makes total sense. Makes total sense. Binary trees are terrible for cache. I'm not sure they're the right thing to use in the benchmarks game. I think that it's like, that's a fair point, Nadia, but there it doesn't make sense. How do I want to say this? Benchmarks don't need to be written to be fast. Ideally, they're just written to be practical, right? So we did I covered the same thing in the last benchmark I was optimizing, which was recursive Fibonacci. It's it's frustrating actually, but so many people, while I was optimizing the recursive Fibonacci, and then after, when I published the blog post on the recursive Fibonacci, they're like, oh, well, you can write recursive Fibonacci even faster if you do it this way. You know, if you change the way that you are writing the recursive Fibonacci, it will be even faster. And I'm like, that's not the point. The point was to take a naive recursive implementation of Fibonacci and compare the performance between Jank and Clojure JVM, and to have Jank perform faster in that naive polymorphic version of Fibonacci than in the Clojure JVM version. So because that's just like the simplest sort of Fibonacci that someone would write. Now, of course, we do want to support ways to intentionally write things without boxing and without the polymorphism, so that way people can go even faster. But we also need to handle like the dumb stuff too, because a lot of the code that people write is dumb. That's just the truth. That's just the truth. Make things go fast, doesn't matter what the thing is. Yeah. Okay, so we have an object file, but the object file fails to load. Let me do this again. And we're gonna catch the row. Yeah, I mean, you could also have a compiler that's like, oh well, I've detected that Fibonacci is just a pure function, and you're invoking it with a literal, and so I'm just gonna like constant fold that away. But that also misses the point. That also misses the point because it's not about folding that away. It's about doing that work quickly. Yes. Okay, so we have definitely hit a point where our var deref pass has broken some code in closure core. And what we can see here is we have closure core atom, and we are invoking it before it's been defined. Like, or the var has been interned, but we haven't actually, it's been before it's been bound. We haven't actually given it a root yet. And so we're invoking it. It has this unbound object inside of it. And we're saying like, okay, we're invoking atom with one argument and it's unbound right now. And so we don't know why. We need ideally to reproduce this in a smaller scenario. Atom is such an odd one because like that's not even used much. Like where is, oh, is this a macro thing? Is this a macro thing? Is DJ Blue right? This is a macro thing? About to get super eager. I imagine this might have something to do with, okay, so that does work fine. But yeah, then we still don't load it properly. So let me try to do this one more time, but without eagerness and with debug symbols. Should we disable the pass if the var is unbound? No, because the var is not unbound when we do the pass. Like there's no way closure core atom is unbound when we do this. This is about AOT compilation. So AOT compilation is about setting up some code that's going to run later when you invoke a program. And when you start the program, the var after its intern starts out unbound. Oh, DJ Blue. Do we have source info now? Okay, everyone, I just want to call out this stack trace that we have. This, for the very first time on stream, is closure code showing up as source info on a stack frame. So we can see here that we have closure core.jank and closure core.jank. And when I go to frame 2, we actually get to see the source info here. When I go to frame 3, we get to see where this is used right here. This work was added by DJ Blue very recently. So this is the start of us being able to view these values in GDB, step through Jank programs in a debugger, everything like that. He's done some more work to get this hooked into VS Code as well, which I think is a better UX. I just don't use VS Code. But yeah, shout out DJ Blue. Nice work, my man. And let me get out of here. So we do have this atom, and we're invoking this top level. Okay. So I think this should be enough to reproduce the problem. Let's take a look at something like temp AOT. I'm just going to do hoist. We'll call this atom as well. And let's say it takes in a number. And yeah, we'll pull out the, okay. Now this was doing a def once. So we'll start out with a def once as well. And I believe that was doing a map. Oh, it's gone now. Oh, right here. Yes. That's a set. It's one of those things. So let's take this and let's compile it. So args jank phase 1, compile module path temp, and then we called this hoist. Also, all that work is under this new debug flag. Debug flag, not debug. Yeah, so we can, we need to, we don't have closure core. Okay, so I will remove the loading of closure core. I'm gonna remove that from both these because I don't actually know which one we're in right now. Okay, so clear, run. Is this the same problem? I don't know. We're still loading closure core. Why? I'm doing jank phase 1. I'm doing, oh fuck. Doing compile module. Compile module. This one. I hacked the wrong function. I hacked the wrong function. Sorry. My bad, my B. Let's see. Debug, yeah. Remove, yeah. Okay. We should be good now. So can we compile this? Yes, we can. Can we run this again? Fuck. That works. It works all too well. Let me just yoink some print line goodies. And then we can bing bong this. Bing bong. Here's our bing bong. Here's our bing bong. Fuck. Okay. So using this top level atom is clearly not the problem. Is it? Ah ha ha ha. Look at what def once does. Is this the problem? Def once, it does a def of the var to intern it without a value. And we get back the var as this v pound. And then we say when not bound, and bound checks if the value inside is of the type unbound, then we do a def again, but this time with the value. Is this the problem? If we take this, we don't have def macro, but we have def. And we can make something a macro by ignoring the first two parameters and then saying macro. And we can't syntax quote because that relies on the existence of some other shit that we don't have. And so, fuck. Yeah, putting this together is gonna be a pain. Operating without closure core is a real pain in the ass, but we'll make it work. So where's the opposite of the list function that takes in variadic stuff and then gives me a vector? I don't think there is such a thing. I guess I'll just bring in vec and then I'll use list and then vec. So that way I can do a vec here, change this guy to a list, and then yeah, we'll just use v, and then this will be a list of def and name. This will be a list of when not. No, this will be a list of if bound be. I think we can actually just quote that whole thing. And nil, and then otherwise list of def name and exper. All right, that's pretty hacky. Let's see. Unable to resolve name, very helpful error. Okay. Very odd because there's name right there. Def, right. We don't have defen. Perfect. Exactly. Yes, and then we don't have bound yet. So now we just need to grab bound. Bound takes in variadic right now, but let's just change that to v. That way we don't need to do every, and then we can just say v. And then similarly, we'll have to do this. Okay, bing bong. So this works. Now, does it fail again when we load? No, it doesn't. What's the difference? What's closure core doing that we're not doing for this? It's private. That shouldn't matter. Doesn't matter. Is it used? Is that the problem? It's used here. In another def once in a delay. Right, we don't have deref. Deref is not much, actually. It's just this. No difference. Okay. Well, if we can't reproduce it outside of closure core, we're gonna have to just use closure core. Fuck. Yeah. So what we can do is we can generate, let's try to generate closure core to, let's see, where was I? Let's generate this to a CPP file. And so this should give us a core.cpp, and then we'll try our luck at Clang format on that. Clang format doesn't handle lots of C++ very well, and so it ends up just kind of dying oftentimes. I've done some work to try to make our code a little more friendly. Let me take a look, verify we have the right thing. So that should be in target closure. No. Oh yeah, because I put it in core libs. Build core libs closure core.cpp. That's this guy. I'm gonna yoink that out, and so I just want to copy that guy here, and that's fine. Yes. So let's do a format. Actually, what's the size of this? Just so I know before we start. 4. Wow, that means that removing all those extra var derefs actually cut off 900 kilobytes. Okay, not bad. So we're able to format that. I tried to jump to the matching curly for this, and now Vim is frozen because it's searching up 87,000 lines to try to find where the matching curly for this is. My bad. Shouldn't have done that. Well, let's see. In this view of the 40 lines that we can see, is the problem here? No. Let's see where we are binding Atom. So here's where we intern Atom. This is meta. There's nothing going to be in this because this is all metadata. There's nothing else that's going to be in this function. Yeah, and then we have our Atom var up top. So if we search up from here, here's where we take Atom and we bind its root. We bind its root to be 486, which is this function here, with arity1 being closure core Atom. And now, so let me set a mark right here. Now, where are we doing tap set? So tap set is this Atom right here. Tap set is where we grab this, we set our meta, and then right here, so we intern 2856, we intern this. We bind the root to this, which is here. Oh, fuck. This G underscore, we know from looking at the optimization pass that this is from like replaced vars, right? Or like replaced var derefs or replaced, or like synthetic would be the term, synthetic literals. And so this guy is at the very top. And so here's our problem. We're dereffing this guy at the very top. Why didn't we reproduce this issue? In our example. In our little test case, why wasn't this reproduced? So, yeah, we have a couple of things to sort out. Like the first one is, just getting a simple reproduction of this problem. And then the second one is this a general problem or is this only related to the special module load functions where we're actually like, these are the functions where we're actually interning these vars and giving them their initial values and everything. Most functions, like this is a function that's generated by the compiler. It's not actually part of the, it's not actually a part of the code that the application developers are writing. It's just sort of plumbing work that goes on behind the scenes. So it's possible that we just don't run this optimization pass on those load functions because we need them to not like move things around and reorder things. I'm not sure yet. I am not sure yet. Yeah, because it's in this function that Atom actually gets defined. We're in Jenk load closure core 0. And right here is where it gets defined. And right here is where we are. So we, 74, it gets defined at 74,500. And then it's used at 77,000. So it's further down. But because we ended up pulling out the, because we ended up lifting up the var deref, it gets derefed before it's actually filled in. So we might just want to disable this for jank load functions. If I were to just hack that in, something like this. If function name starts with jank load, because all of those do. That's like a well-known path, well-known function naming. Then go ahead and return. Okay. Let's do build core. I think we might be good now. So we have core.o, which we did have before, and now we're using that to compile the nREPL server. Are we going to get another? If we get another .o here at all, then I think we're golden. Let's see. Let's see. We got the CBP file. And then we don't get it because I disabled the loading of closure core during compilation. And so then that fails. I think we're good. So is this the fix that we want? I think so. Because in these functions, in these jank load functions, we don't want to shift anything around because we haven't initialized the namespace yet. Like we're still putting all of the vars together and giving them the metadata that they need and giving them the values that they need. And these jank load functions run only once. So these aren't the functions also that we're trying to worry too much about, like optimizing the runtime for. So not a big concern to skip this pass on those. Like, I don't think that's going to have that's not going to have an impact on the, like the ray tracer benchmark, for example, because that's going to run once, and that is not even going to be part of the code that we're benchmarking, because the benchmarking suite is going to kick in afterward. Yeah, so we just compiled all of those files. If we were to jump back to this, we have CPP files for all of that now. And so now we just need to compile those CPP files. Where did your idea to write a custom Clojure dialect come from, Johnny? Well, I already wanted to work on my own programming language, and that's what I spent several years doing, was just exploring programming language design, because I was doing a lot of C++, and I was hitting limits. I was trying to go places that C++ wouldn't allow me to go, and so I wanted to branch out. And so I just started exploring, like, what would a language look like that allowed me to do all the things I want to do. Ideally from C++, keeping all the C++ stuff, but then doing more on top of that. And then that led me to getting into functional programming and trying out like Haskell and OCaml, and got into Common Lisp, and did a lot of Rust. And then I found Clojure and wrote a lot of Clojure, and then was like, okay, yeah, I really like this Clojure thing. What if I did a Clojure thing, but kind of made it C++-y? And so that's when, about 3 years ago, I was like, all right, so I know I want to do a language. I know I want it to be C++-y. I know I want it to be Lispy. What if I do a Clojure dialect on C++? And I kind of take the two of those. Do I like Rust? Yeah, I think Rust is great. Rust is great. Okay, so that's everything. Can we run the ray tracer? Jenk run O3 eager, and then ray. I don't think we need anything more than that. And so then the following question, after asking me if I like Rust and hearing me say yes, is, well, why am I building a Clojure dialect that has C++ interop and not Rust interop? Yeah. And the answer is, given the compilers that are around for Rust right now, there is no JIT compiler for Rust that's viable to make a Clojure dialect out of it. And so it's like, if you wanted to make a Jenk except in Rust with seamless Rust interop right now, I don't think it would be doable, because there's no viable Rust JIT compiler. And then on top of that, like, with all the borrow checking semantics and safety checks that Rust has, like, I don't know how that's going to work with JIT compilation in this sort of environment. Maybe it will. But certainly in terms of compilers, there's just not a viable compiler to make this whole thing work. Like, being able to JIT compile C++ is what makes Jenk possible. And it wasn't until very recently that work for the JIT compiler was upstreamed into Clang and LLVM. Before, it existed separately as a project called Cling, and that's what Jenk was using. C++ needs all the help it can get. Carp, have I heard of Carp? Yeah, Carp's cool. I haven't used it, but I've read their docs a lot, and I really like the stuff that they're doing. Okay, so 35. This is not a big win. Just use an LLM to rewrite libclang in Rust. It's not libclang. Libclang is not what does the JIT compilation. We don't use libclang, actually. It's the whole Clang JIT compiler. I know you're just being facetious, though. Frondophobic. I think that one thing that really appeals to me, because like I like C++ in a silly way, you know, like I like Rust a lot. I think it's a great language. C++, I like the power that it has, and what it gives me, what it allows me to do, and the APIs that allows me to make, when accepting that power and taking advantage of that power. But I don't like the concern of all of the possible like undefined behavior, and then the outcome of that, the implications of that. And so I think that Phil C and Phil C++, which are created by Phil Pieslow, I think those are really, really exciting, really cool, because Phil has basically, he's forked Clang 20, and he's built a runtime for C and C++ that is memory safe. And so that means that if you have any sort of like array out of bounds, or use after free, or any like uninitialized value usage, or any sort of undefined behavior, it will either normalize that to well-defined behavior, or it will panic. That's it. Like, and you have, I think, I don't know if they go as far as guarantees at this point, but the goal is like guarantees. I think that there's a very high level of confidence in these, in the runtime at this point, to where you're just like, yeah, this is not going to be exploited. If someone manages to trigger some like return value exploiting, where normally you would be able to choose where you want to return to some particular shell code that you've written somewhere, and then you exploit that. If someone were to do that in a program compiled with Phil C or Phil C++, it would just panic. And you still get to write all that code in C, C++, whatever you want to use. You have to pay a runtime cost, performance runtime cost, which I think is like, I don't remember the numbers. I think it's like 20% or something like that. And that number keeps shrinking. It's like, I think there's always going to be a runtime cost, compared to what Phil calls YOLO C and YOLO C++. But the idea is that you don't need to rewrite your millions of lines of native code. You just need to run it in a safer runtime. And then categorically, you don't have to worry about exploits. And if you have memory errors, worst case scenario, it just ends up being a panic. That, I think, is the future of C and C++. And that would also mean that it's the future of Jank. So I imagine in the future, you would probably run Jank on Phil C++ by default. And so by default, Jank will just be memory safe. If you fuck something up, you don't need to worry about, you don't need to worry about in your applications or servers, those fuck ups being exploited, aside from potentially just crashing the process, which is very different from getting remote code execution, right? So it's potential denial of service attack, but you bring the service back up, and there you go. Like, that's also possible in the JVM, for example, to just bring it down. But if you wanted to squeeze out that extra performance, and you're like, yep, YOLO, then you would be able to say, okay, compile my Jank project with YOLO C++ instead, and then you are, responsible for whatever happens as a result. I see that as the future. it's not the case right now because Fill C is based on Clang 20, and Jank requires minimum Clang 22 to even work because of all of the stuff related to the JIT compiler that we've identified and had to fix or have had others fix for us. But yeah, when we get to a point, hopefully, where Fill C run on Clang 22 or more, then we would, and I don't know how their JIT stuff works. Like maybe I'll need to work with Phil to make that, maybe Phil and the Clang guys to make that work. But that's the future. So yeah, we'll have C++, interop will have a C++ runtime, but it will be memory safe. I think that's the way. Why is this not faster? Why is this not faster? I wonder, let's print out, can we do that? I kind of want to print out stats to show like how many bar derefs we're alighting so we can get an idea of the work that was done. Does a ray tracer have a lot of loops? I don't think so. Let's take a look. So that's a loop. That's a loop. This is not a loop. Rand ray create vec3 add vec3 scale. So in this function, like we should certainly be able to clean up some. In this function, because we have these loops, no. This is a reduce, so there's no loop. So this function, like all these vec3 creates, this is just startup though, like setting things up. Raycast, no loop. A few like vec3 creates here. Like I would imagine that these get cleaned up into one. No loop in this one. But vec3 create is really the only thing that we're repeating. No loop in this one, but no vars that are repeating. No loop here, no repeated vars. No loop here, no repeated vars. No loop here. We do have some like vec3 dot, vec3 sub are used 2 and 3 times. So no, we don't have a lot of loops, and like none of these are using loops as we go up here either. And we have a lot of vars that we're using. But not necessarily a lot of duplication. Damn. That's a little disappointing. I mean, that's how it goes with these optimizations though. Like you don't always get good hits. I was expecting this one to be a hit. I was expecting this one to be a hit. Let's take a look at the generated IR. So let's do a jank print IR, one. And we'll put this into... Oh, fuck. I need 2 to get the optimized one. Which objects can Jank currently represent during some pointer masking techniques? 32-bit integers and all doubles. Everything else is a pointer. So anything greater than a 32-bit integer, and anything that's not a double. Ray IR. Ray IR. So let's take something like, where were we seeing? Yeah, let's take something like hit sphere. So we can see here a lifted literal. We can see some knopping. We can see some knopping. Let's see what's going on with these var derefs. So we have a var deref for sub here and length squared and dot. These are all inside of entry. We have a var deref for squirt here and var deref for ray at and vec3 div. Vec3 create. Yeah, so we did end up reusing, so if we look at sub, we did end up reusing these. So yeah, the optimization has certainly applied. It did apply to the IR. Just didn't have the effect we wanted. Oh well, it's still a good thing to do, because it's less work to do. It just doesn't help us out with this particular benchmark. We could certainly write benchmarks where it would help, but it's significantly less code. It was, I mean, this is a big enough win already. Check this out. Wait. Build core libs closure core CPP. Oh, fuck yeah. So we're down to 3.5 megs. Where we were at when we started was 5.3 megs. So this is worthwhile, even if it doesn't affect the runtime performance of this particular benchmark. It's worthwhile enough because it removes, like, what is that? 1.8 megs. Those two optimization passes remove 1.8 megs of code from closure core. Is that right? Is this formatted or not? It's not. So yeah, that is right. Would that improve compile times? Absolutely. Yeah. So this is like, that's a really big win in terms of compiled code, which absolutely improves compilation times. So if you are down, if you're feeling downhearted about the benchmark results, don't. Because let me tell you, like, that's a big fucking win. Yeah, 1/3. Yeah. Anything I can do that gets this number down for Clojure, like Clojure core compilation, that's huge. That's huge. So yeah, let's take that a step further. I'm gonna step away for a restroom break, and then let's do one more pass, maybe two. We're gonna do a pass to eliminate some dead code for loops, and then we'll see if we have time, how I feel, to do a pass to eliminate the nops. The nops aren't gonna help us with this. It's just gonna clean up the code, so that way we don't end up with like, because if you look at this one here, like nop, 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 nop. We got a lot of nops here. So ideally we just don't have all those, and we can clean that up. So I'll be right back, and then we'll do our second win. All right. Yeah, this is a surprising win. Like I expected it to help, but I didn't expect it to help that much. And when I think about it, I know where it's helping. There's a particular code pattern that emits quite a bit of var usage, and it's syntax quoting. And so that, like any macros that we have in Clojure Core, there are quite a few, just have a huge amount of like code bloat. And so that ends up being optimized, where we just do one var deref for all of that stuff. And that's great. I'll take that. And it's not slower for runtime. It's just same speed. So let's get a pass written that covers a different use case. It's probably not going to help us for the ray tracer, but it is something that I want to get done because it is going to help us in terms of code size. And it's just a good thing to do, I think. So it's one of the things I wanted to do while I was writing passes, which is right here. So let's add another pass. And what I'm going to do is I'm just going to take this and I'm going to do that. I'm going to do a tab new right here. And I'm going to, I'm going to say, I don't know if this should just be part of dead code elimination, but let's give it its own thing for now. So I'll just say like eliminate branch set redundant branch set. Okay. And then inside of here, let's yoink all of this, but it's going to be a lot less than this. So we don't need to collect anything. Eliminate redundant branch set. We don't need to worry about this. We don't need to collect. We don't need to worry about this. What do we actually want? So for this one, let me show you the use case. The use case, I'm going to keep all these test cases around because they're going to be useful later on. The use case for what we want here is, let's assume that we have a loop. I'll just use a normal loop like that. And then we'll have like A1 and B2 and C3. And if C is equal to 10, then we're done. Otherwise, recur with A and B and inc C. This is kind of this is a simplified example of it, but this is what we're going for. And so if we do a jenk print ir, jenk run test.jenk, then so we're going to see we have we have our entry here. Also, I suppose I should do it too. Here, doesn't actually change anything here, but we have our entry loop, our entry block. We enter a loop right here, and so we have a loop block where we actually do our work, and then we do a branch to check if we're done. So here's our loop. We have our loop block. We have a branch to check if we're done. Now, when we recur, we're going to mutate the variables. We have A, B, and C. We're going to mutate the variables for A, B, and C. Now, when we don't change the variables and we just recur with the variables as they were, we end up with branch sets where we're setting, in this case, like S7 to S7. You know, maybe we just don't even need a pass for this. Let me, before we do a pass, let me take a look at IR processor and see if we can just be smarter about this. Loop ref. Let ref. So here's our loop block. And then we want a recur ref. So right here, we end up doing a branch set. So I think what we will just say is, if we just do like shadow, yeah, you know what? I think we could do this without a pass, which is even better. So this is shadow, and then this is new val. And what we'll say is if shadow does not equal new val. I think that's it. And so what that's going to do is it's going to eliminate these two. And when we take a look at the generated code, jank print code gen equals 1. Right now we're just doing, you know, S7 equals S7, S8 equals S8. And like, this might be allotted by the compiler depending on the type. Since we actually have overloaded this for this type, I worry that it may not even be alighted. But even if it's not, or even if it is allotted by the compiler, it's extra code that we need to end up compiling. And I don't want to do that, because like compiling C++ is our biggest problem. It's the slowest thing that we do. Wow, that's amazing as well. So for anyone who is watching in previous streams, like for release builds, we were waiting like 3 times longer or something like that to build nREPL server. So I think from all of this code gen, like from all these optimizations that we've done that has impacted the code gen, this has actually really lowered the compile times for release builds. I love that. Cool. So now we just have S9 here. There's no need to set that at all. Cool. So no pass needed for that one. Let me, I don't know if I saved this file, but let me just delete that and then eliminate this guy. Let me delete that. And then do I have this? So I will just remove that. Cool. And so that was super easy. All right, last thing is let's actually write a pass, and this is actually going to be a pass, to just remove the knobs. That's going to clean things up. That's going to clean things up nicely. So I'm going to do remove knobs. And I'm not going to copy the other one for this, aside from the includes. We don't actually need any of those, just that, I think. So to remove the knops, all we're going to do is, if we loop through all of our blocks and then loop through all of our instructions, then, so we can't use a range-based loop because we're going to be modifying this as we go. So we have to do a use size I is less than function, nope, I is less than block instructions dot size, and we won't do a plus plus I here. So we'll do a plus plus I at the end, and then we'll say if, so actually let's just grab our instruction. So autoconst int is block instruction sub I. If inst kind is equal to instruction kind nop, then we're just going to do a block dot instructions dot erase, and erase takes has two overloads. I think we can just give it an index. If not, we need to give it an iterator. It takes an iterator. So we need to do begin plus I, block instructions that begin plus I. I would expect this to work. Block is const. Okay. I think that's it. So let's do remove nops, and then this is IR processor. So we'll do remove nops. Whoops. I didn't include that file, and also I kept the pragma once in the CPP file. So I'll include remove nops. Nice. Okay, so this is a bug. This has a bug right here because in the case where we remove the instruction at the current address, we don't want to increment I. That's why I separated I out here, but I forgot to continue right here. Yeah. And so basically, if let's say I is 0, and the 0th instruction is a nop, so we remove the element at index 0, and then we continue. And we want our index to stay at 0 because then the next thing we're going to look at is the thing that was after the thing that we just deleted. Yeah, in terms of those two optimizations, I don't think it's going to have a huge impact on the generated code size. So we were looking at it was 3.5 before. Yeah, it's still 3.5. So not a huge difference there. But when we take a look at our test here, so we did have, well, I don't know if we had NOPs in that one, but we definitely did in this one. And now we have no NOPs anywhere. So our var deref has been lifted up here for print line, because this is the one where we have 3 print lines and then also 4 5s. And our 5 is here, and that v3 is used throughout. And not was also lifted up, but all of the old instructions that have been that were knopped out and then were the uses were rewritten, those are gone. So I'm pleased. I would be more pleased if the var deref optimization ended up having a huge impact on performance, but it didn't. That's okay. Because I will take, what I absolutely will take is cutting off 1/3 of the generated code size. And with the release builds like flying, as quickly as they are, yeah, compared to what it was in previous streams, we spent a lot of time sitting here waiting for those builds, and they do all the same shit now, like they have all the same behavior that they had before. We're just generating less code, and I will absolutely take that. So yeah, doesn't move us closer on the benchmark, but absolutely moves us further in terms of the quality of the compiler and the viability of the compiler for large Jank projects. Anybody who's working on a Jank project right now, like Cameron working on the game engine, or Doug working on a Wayland compositor, like these wins are already going to have, or these changes are already going to have big wins when it comes to compiling their code, AOT compiling or JIT compiling their code. So yeah, that's great. And also it feels good to like use the IR. And it's not difficult. It's not difficult. Like, I want to see how this stuff can be deduped, so that ideally this pass can just focus, like the logic for the pass can just focus on like find these things, replace them, and then maybe like have all of the other stuff for like knopping and everything, where to place them, everything like that. Like maybe all of that can just be moved into helpers. That way these passes are really easy to write, and they're like 150 lines is not bad. Like if they all have to be 150 lines, because it's relatively straightforward code, I would take it. But yeah, if I can get this to like 50 lines, I would prefer that. And one of the things I know is like, if it's easy to do something, in terms of UX, if it's easy to do something, people are going to do it. And so I want it to be easy to write these optimization passes, so that we do it more often. Because there are a ton of different passes that we can write, and a ton of different benefits, not only in terms of runtime performance, but also in terms of compile time performance that we can get out of it. All right. Well, we did the hoisting of the VAR derefs. We did the removing of the knops. We did the alighting of the duplicate branch sets. We talked a whole bunch. We'll call it a win for today. I appreciate all of you. Thanks for hanging out. Pat10, thanks for that new sub. You're great. I will catch you all next week. Have a good one. Adios.